Hello and welcome to Call of Chemistry. In this video, we will discuss about an easy trick by which you can easily convert the zigzag projection into Fischer projection and vice versa. So firstly, we have to know what is zigzag projection. So such type of representation or projection is termed as zigzag projection. So in this zigzag projection, we can see that this OH is above the plane, this BR is below the plane, this fluorine is below the plane, and this OH is above the plane. Now how can we convert this into Fischer projection? We will discuss the step-by-step method. So firstly, we have to do numbering. So this is number 1 carbon, this is 2, this is 3, this is 4, this is 5, and this is 6. So in the first step, we have to assign the absolute configuration or RS configuration in this 2 numbered carbon. So we have to assign the priority sequence first. So this is 1, this is 2 numbered group, and this methyl has 3rd priority. And the hydrogen has the least priority, that is 4. So if we assign RS configuration, that should be 1, 2, 3, and that is clockwise direction. So this should be R. Now we draw the Fischer skeleton of this compound. Here is CH3 and here is CH3. This is 1 numbered carbon, this is 2, this is 3, this is 4, this is 5, and this is 6. Now notice, in 2 numbered carbon, the absolute configuration of the 2 numbered carbon was R. So we have to place the OH group in such a way that in also Fischer projection, the absolute configuration of 2 numbered carbon is retained, that is R. So if we draw OH here, then here will be H. Now we have to check the absolute configuration of this 2 numbered carbon. So this has 1st priority, this has 2nd priority, this has 3rd priority, and this hydrogen has least priority, that is 4. So we can see that it's 1, 2, 3. This turns clockwise, but as least priority hydrogen is in horizontal position, so it reverts to S. So here we see that in zigzag projection, the number 2 carbon was in R configuration, but here in Fischer projection it is S configuration. So this representation is wrong. So we have to place OH in here, that is left side, and H should be in right side. Now we will check the RS configuration, that is, this is 1 priority, this is 2 priority, and this is 3rd priority, and this is the least priority, that is 4. Now this 1, 2, and 3 turns anti-clockwise, but as hydrogen in horizontal position, then it should be in R. So OH should be in left side in Fischer projection, and that is correct. Now the trick comes here. I am writing the trick. That is a special one. Look very carefully about the trick. So in the trick it is said that stereochemistry of groups in zigzag projection, if it is same, then the position of groups in Fischer projection will be opposite. So here we see that this OH in above the plane and this bromine is below the plane. That is, in zigzag projection, the stereochemistry of 2 adjacent groups are opposite. So in Fischer projection, according to the trick, that is opposite, same. So this BR should be in same side in which OH resides. So OH in left side, so BR should be in this side. Again I repeat that in this trick it is said that if 2 groups, that is 2 adjacent groups, are in opposite in zigzag projection, then those 2 groups will in same side in Fischer projection. So here we see that this O is in above the plane and this BR was in below the plane, that is two groups with two opposite stereochemistry. So here in Fischer projection, according to the trick, opposite turns to same as in Fischer projection, so OH and BR should be in same position. Similarly, this BR and this fluorine in zigzag, they are in same stereochemistry, so same turns to opposite, so fluorine should be here. Similarly, this fluorine and this OH are in opposite stereochemistry, so opposite turns to same, so OH should be here, and we keep hydrogen in alternate position. So this was the trick of converting zigzag projection into Fischer projection. So firstly, we have to assign the RS configuration of two numbered carbon. Then we have to place OH in Fischer projection in such a way that the absolute configuration of two numbered carbon will be the same. Then we will follow this trick, and accordingly we will find that this structure corresponds this zigzag projection. And this is the Fischer projection. Now we will take an example of Fischer projection and we have to convert this into zigzag. Suppose we take D-glucose. So here H, here is H, this is now firstly we have to assign the RS configuration of this carbon. So this is one priority and CHO has second priority, this has third priority, and this hydrogen has fourth priority. And we see that 1, 2, 3 anti-clockwise direction, but hydrogen has least priority in horizontal position. This reversed to R. Now we draw the skeleton of zigzag projection of D-glucose. So here it is CHO and it is CH2OH. Then we have to assign this OH group in this carbon in such a way that this carbon contains the R configuration. So we have two options, either we can write in above the plane or we can write in below the plane. Let's see what happens if we place in above the plane. So if we assign the RS configuration and firstly assign the priority sequence, it will be 1, it will be 2, it will be 3, and the hydrogen that is in least priority, that is below the plane. So 1, 2, 3 and the anti-clockwise, so it is S. So it is wrong, so we have to assign OH in below the plane, and that's the way only this carbon will contain R configuration. Now we check the absolute configuration of this carbon. So this is 1, this is 2, this is 3, and hydrogen is in above the plane. So this is 4. So 1, 2, 3 anti-clockwise, but hydrogen which is least priority and it is in above the plane, so it is reversed to R. So if we assign OH in below the plane, then this carbon will correspond the R configuration. So this representation is correct. better we are this double-headed arrow. Now see, this OH group and this OH group in Fischer projection, they are in opposite side. So if opposite side in Fischer projection, then it turns to same in zigzag projection. So the stereochemistry of the two adjacent OH groups will be same stereochemistry. Then OH should be in below the plane. So similarly, this OH and this OH are in opposite position in Fischer projection. So in zigzag projection, it will be same stereochemistry. So it will also contain below the plane stereochemistry. Now this OH and this OH are in same position. So same turns to opposite. So these two OH contains the opposite stereochemistry. So this will be in above the plane. So this is the zigzag projection of D-glucose. If you want to enroll yourself in online or offline classes, you can contact over this number. So by this I am stopping here. If you have any doubt, please let me know in the comment section. Please like, share and subscribe my channel. Thank you.